Often we're concerned not with just how much work is done, but how quickly the work is done. And the quantity that describes this is the power. The power is the rate at which work is done, or the amount of work done per unit time, or the definition I have here, which is the change in energy per unit time. Each of these definitions are equivalent. So if we write out the expression for constant power or average power, it's power P equals delta E, the change in energy to the system, per unit time, delta T, or the work done per unit time. And again, these are equivalent. So the unit here is energy or work, which is in joules, per second, and this is defined to be called a watt. There's one more definition of power that is sometimes useful. For an object traveling at a constant velocity, which is acted on by a constant force, we can write power equals work per unit time, and then work is Fd cos theta over delta t, and then we can replace the distance over time by the speed since it's constant in this case. So we have power equals Fv cos theta. So again, this expression works if there's no change in energy to the object. Example 19, a 1600 kilogram elevator is raised at a constant speed through a vertical height of 20 meters in 8 seconds. What is the average power output of the winch hauling the elevator upwards? All right, let's use the definition for power with the change in energy, since we can clearly see there's a change in gravitational potential only in this case. And this is because it's moved at a constant speed upwards, so a constant velocity, no change in kinetic energy. So the energy that's changing is going to be gravitational potential energy per unit time, which is mg delta h over delta t. And then we can plug in the numbers to find the power. So we have a 1600 kilogram elevator times g, 9.8 meters per second squared, moving up 20 meters in 8 seconds, which is 39,200. We have energy on the top, joules per second, which is a watt, and that's the SI unit for power. So I just want to point out that this was moving at a constant speed and experiencing a constant force, so we could have used this definition, P equals Fv cos theta, to find the power. It would have looked very similar to what we had here. So because it's moving at a constant speed, Fa equals Fg, which is mg. So we could do this in steps, 1600 kilograms times 9.8 meters per second squared, and that's 15,680 newtons. And then we have the speed is the distance over the time, so that's going to be 20 meters over 8 seconds, so 2.5 meters per second. So you can kind of already see we have the exact same formula as here, mg times delta h over delta t, but let's just plug that in. This is cos of 0 because they're in the same direction, the force is in the same direction as the velocity, that's equal to 1. So we have P equals Fv, which is 15,680 newtons times 2.5 meters per second, which again gives us 39,200 watts. Example 20, A, how much work is done in 1 hour by a 1 kilowatt power source? B, if this was used to power a perfectly efficient crane, to what height would this crane lift a 1,500 kilogram car? All right, so in A, we're given the time, delta t is 1 hour, so 3,600 seconds. And then we have the power, it's a 1 kilowatt power source, so this is 1,000 watts, or 1 times 10 to the 3. And it says how much work is done. So work, we've seen power equals the work done, or the change in energy per unit time. So the work equals power times time, 1,000 watts times 3,600 seconds gives 3.6 times 10 to the 6 joules. And this example is here really to define this unit of energy, which you may have heard of before. A kilowatt hour it's written like this: 1 kilowatt hour is equivalent to 3.6 times 10 to the 6 joules. And this is a conventional unit used to measure energy. Though it says watts, it's multiplied by time, so this is a unit of energy that is used for large amounts of energy. And it's often used for electrical energy, so this is something you would see maybe on your hydro bill. Alright, so for B, if this was used to power a perfectly efficient crane, to what height would it lift a 1,500 kilogram car? So now this energy is being used to cause a change in gravitational potential energy to the car, so it's equal to mg delta H. So delta H will be equal to the work done, or delta PEG, over mg. So 3.6 times 10 to the 6 joules over 1,500 kilograms times 9.8 newtons per kilogram, or meters per second squared. And that's 245 meters. Machines or processes don't typically convert all of the energy that they take in into useful energy output. So how we describe this is by using an efficiency. The efficiency is the ratio of the useful power output of the machine or the system to its power input, and that's the energy that it consumes per unit time. So we can write this efficiency ratio, E, as P out, the power output, that's the power that goes into doing the physical task, over the power input, which is the energy consumed per unit time to the machine. Or, since this all occurs in one time period, time would cancel if we were to change this to work done per unit time in both the numerator and the denominator. So we can write it in terms of work done or in terms of change of energy to the system. So it's also equivalent to the work output over the work input, or the change in energy out, so the energy that's leaving the system to do the physical task, over the energy in, the energy consumed by the system. And this will give you a fraction, or a decimal, which is the efficiency rating of that machine. However, we can also multiply it by 100 to convert that to a percent. So machines are not perfectly 100% efficient because some energy is always lost, whether it's because of friction, air resistance, or heat, sound, or maybe as exhaust. There's always some type of energy that's lost during the process. One unit that you might see while working with power other than watts is horsepower. We still commonly use that to measure the power of some things, for example, car engines. So 1 horsepower, or HP, is equivalent to 746 watts. This is a conventional unit that comes from many years ago when it was used to compare the power of draft horses to steam engines. Example 21, your 1,500 kilogram car is behind a truck traveling at 60 kilometers per hour. To pass the truck, you speed up to 75 kilometers per hour in 6 seconds. A, assuming that resistive forces are negligible, what is the required power of the engine? B, express your answer to part A in horsepower. C, in fact, it is found that the engine's actual power input is 75 horsepower during this process. What is the efficiency of the engine? All right, so for part A, we want to find the required power, so the power that goes into accelerating this car. So this will be a change in kinetic energy per unit time. Now I've written the conversions here, so we'll need 1 horsepower eventually is 746 watts. Then we have 75 kilometers per hour is just converting 20.8 meters per second, and 60 kilometers per hour is 16.7 meters per second. So let's find this change in kinetic energy first. That's going to be 1/2 mv squared minus 1/2 mv naught squared, or 1/2 mv squared minus v naught squared. So I'll write it over here. Delta KE is going to be 1/2 1,500 kilograms times 20.8 meters per second squared minus 16.7 meters per second squared, which is 115,312.5 joules. Now we can divide by time to find the power. It will be that number that we found for the energy divided by 6 seconds, which is 19,219 watts. Okay, that's all for part A. Part B asks us to convert that to horsepower. So now we'll have 19,219 watts times 1 horsepower over 746 watts. So dividing by 746 is 25.5 horsepower. And now part C is asking us for the efficiency. This is the power output. We find that the power input is only 75, or is actually 75 horsepower. So the efficiency is going to be power out over power in. We'll multiply by 100 as well to get that to a percent. So this is 25.5 horsepower over 75 horsepower times 100. Gives me 34%. It's really not unusual for a car engine, actually. They have fairly low efficiencies. Example 22, to accelerate a car from rest to 5 meters per second requires a total work of 164 kilojoules. Assuming that the vehicle is 55% efficient, what is the required power rating of the motor if it takes 2 seconds to accomplish this task? State your answer in horsepower. All right, so we're given the work output, the energy that is used to doing the physical task, which is accelerating the car. And then we have the efficiency. It can either be written as a decimal like this or as 55%, and the time is 2 seconds. Eventually we want power, so let's convert that work output to a power output right away. Power output is the work output over delta T. So 164 kilojoules over 2 seconds is 82 kilowatts. And then we have that the efficiency equals the power out over the power in. So if I solve for the power in, it's the power out divided by that efficiency. So that 82 kilowatts divided by 0.55. And then this gives me 149 kilowatts. Okay, the last step is to state this in horsepower. So 149,000 watts times 1 horsepower over 746 watts is equal to 199.73, so 200 horsepower.